Welcome to This Explainer. Today, we're going to take some highly formal, theoretical computer science concepts and absolutely transform them into an exciting blueprint for modern software. Seriously, if you've ever wondered how the abstract mathematics of computer science actually translate into the code that runs our entire world, well, you are in the exact right place. We're focusing on introduction and regular languages. We're going to apply fundamental engineering principles to analyze and construct the very building blocks of machine communication. It's a journey from the absolute microscopic building blocks of data all the way up to massive real-world applications. Let's get into it. But before we get into the heavy engineering, I want you to consider this for a second. How does a computer actually read a word? Really think about it. A machine is completely devoid of human intuition. It doesn't have context, it doesn't have a gut feeling, and it sure doesn't understand nuance the way you or I do. Yet, somehow, it manages to process, search, and recognize text without any ambiguity whatsoever. I mean, how does it do that? Well, it does it through the rigid, fascinating rules of formal language theory. So, here is our blueprint for today. 1. The foundation. 2. The rules of the game. 3. The architecture. 4. The mechanics. And finally, number 5, the real world.
Kicking things off with Section 1, the foundation, which covers alphabets and strings.
Okay, so forget everything you learned in kindergarten. In formal language theory, an alphabet isn't just A through Z. It's simply the fundamental finite set of symbols used to construct strings. It could be binary, just zeros and ones. It could even be DNA sequences like A, C, G, and T. These are the raw elemental bricks of our building. We absolutely have to break communication down into its simplest units, because without defining this finite set of symbols first, it's literally impossible for any computer to even begin recognizing or processing data. Now, if alphabets are our raw bricks, well, strings are the walls. A string is just a finite sequence of symbols chosen from that specific alphabet we just talked about. By combining those elemental symbols, we create these sequences, and these sequences act as the foundational walls of all machine communication. Moving right along to Section 2, the rules of the game, where we'll look at expressions and languages. So, we've got our bricks and our walls. But how do we tell the computer which walls are built correctly and which ones aren't? This requires understanding the exact engineering steps to construct a regular language. Step 1, pick an alphabet. Basically, define your raw symbols. Step 2, form strings by combining those symbols into finite sequences. And Step 3, apply a regular expression rule. It's a perfectly logical progression, right? We're moving from raw, meaningless symbols to a highly structured language that a computer can actually parse and recognize. You can really think of regular expressions as the engine that defines those languages. They're the theoretical tool we use to construct and interpret different types of regular languages. Actually, they're the exact mathematical rules that dictate whether a specific string of symbols belongs in our language or, gets tossed out. It's the exact math that lets a computer instantly spot a valid email address or reject a bad password.
Let's dive into Section 3, the architecture, specifically evaluating grammars. We have our strings and our rules, sure, but as systems get more complex, we need architectural blueprints to evaluate problem statements involving language recognition. For instance, we can compare RL, or right linear grammars, versus LL, left linear grammars. Simply put, right linear means our unknown variable sits at the very end of the rule, while left linear puts it right at the beginning. Different problems require different architectural approaches, and understanding this distinction gives you the exact framework you need to analyze and recognize languages efficiently.
All right, Section 4, the mechanics. Let's talk closure properties. Closure properties aren't just abstract theoretical math. They're all about selecting efficient methods to classify and combine languages. By comparing and contrasting various closure properties, engineers can predict exactly what happens when you alter languages. For example, if you combine a regular language of valid emails with a regular language of valid phone numbers, is that new combination still a regular language? Well, closure gives you the answer. Knowing this allows you to select the most efficient method for solving really complex problems. Let's pull back for a second and look at the big picture. Notice how all these concepts beautifully build on each other, going from theoretical objectives straight to a problem-solving engine. We started by analyzing strings, moved to constructing engines with regular expressions, built architectures with grammars, and finally classified them with closure. Tied all together, they form a complete, highly effective engineering toolkit for solving complex computational problems.
And that brings us to our final section, number 5, the real world, taking all this theory to software. This is where we swing the pendulum from academic principles to the concepts that literally drive the modern internet. So where do we actually use this stuff? Text processing and search algorithms. Every single time you search a massive database, or every time a server validates an email address, or strips out bad characters from a gigabyte of text in milliseconds, it's using regular expressions. Mastering these theoretical regular languages is exactly what allows software engineers to build the powerful, lightning-fast search algorithms we rely on every single day. We've gone from the simplest alphabet to the engines that power global search algorithms, and it all boils down to one absolute game changer of a takeaway. If you can define the language, you can control the algorithm. You've got the theoretical engineering principles, you have the closure properties and the grammars. You now understand the invisible mathematical rules that dictate machine communication. So armed with this blueprint, what will you build next?